Data augmentation, that's a weird place to put for regularization, but I guess it does help. So we're not talking about images yet, but you could talk about with any data. Essentially, you want to reduce, yeah, you want to reduce the problem of your model overfitting. Another thing you can do is basically give it more examples, right? So give it more data, it's going to produce a more general model. But what if you don't have more data? So data augmentation is this whole approach of basically creating fake data from your original data so that you can train your model better, right? And so basically you're still just using the data you have, but sometimes it does help, right? In images, it's very easy to see this because you can have a network that's good at learning certain images. We're learning these moths, and it overfits to moths of this color on green leaves facing this way, right? So okay, that's a moth. I'm very good at detecting these moths. But you don't care if this moth is facing this way or flipped left to right or sitting on a yellow leaf rather than a green leaf. Those aren't important to you. You'd actually want it to do well on any of these images, right? But if you don't take steps to regularize your network, it would learn just this and only be good at this, right? And so augmentation is basically a way to say, like, what are the ways to modify my data, randomly distort it or create deterministic new data sets from it that would help us learn better. And they are new data sets, right? So from the point of the neural network's really dumb, right? So people outside who don't do AI are going to learn these things. Oh, it's neural network so smart, it learns so many things, but it's really dumb, right? You're seeing the variables. It's just a bunch of weights. There's no intelligence in there, right? I'm an artificial intelligence researcher. I want intelligence in machines, but a neural network is not intelligent, right? It is a black box function with a lot of weights that we train to optimize some loss function, right? We can use it to simulate intelligence or to convince people it's intelligent, but it doesn't have anything, right? And so it doesn't know that this moth is basically identical to that moth and just flipped. It has to learn that. And so if you give it all these data sets with the flips and all the possible ways of flipping it, changing simple colors, even adding noise that would be reasonable, these are new data. It should be able to learn them a little bit faster than it would from scratch, but this isn't cheating in a way. You're creating a lot of new data now, and you can train your model on all of that, and it will learn something more robust that won't fall into the problem of not knowing about these types of variations. So this could apply to any data set. It's easier to see it for image data, but even for like the COVID data, I guess you could try to modify things. You'd want to modify something that doesn't change the label. You say, oh, I know it would still happen. Maybe I'm just thinking off the cuff here, right? If you have a data set of somebody who got sick in a certain range, you could say, well, we know if they're older, the label is probably still going to happen, right? Certain changes in the data would probably not change the label because we know certain things about the disease or about, say, where people live. And so, having this particular lat-long latitude is going to have one effect, but having something anywhere nearby, if you randomly change the lat long of that person, it's not going to have a huge effect, especially in that data set, because the lat long coordinate is actually the test center of the hospital they went to, not where they live. And so we don't want it to be specific to those coordinates. We want it to learn something more general. So a data augmentation method you could try with that would be adding noise to the coordinates within a reasonable scale, right? So whatever the lat long coordinate for Guelph, it's that town. Anywhere, any coordinate within the region of Guelph, those people are going to be going to that single test center. So you don't care what location it is, right? So that'd be a way to get more data. Okay, here they have early stopping, as I was mentioning before. So you can be talking about your training set loss and your validation set loss, and at some point either it goes up or it flattens, and you say, we might as well just stop here, right? And that means we could have only gone this far to train. And that's probably better than overfitting and going super deep and getting our training data. You'd want to basically stop as early as you can when it's not going to help you anymore on your validation set. So they have some other methods in here. They show dropout using their graph structure. So if we have networks being represented this way with with graphs, then dropout is essentially searching the space of networks with less links in them, and you can see which ones work better. So you can kind of update them as you go, but you could also start selecting ones that are more efficient and keeping those. I guess they're just showing all possible networks here. And there are problems, we'll get back to this later, I think, but there's challenges with this no matter how well you're doing. There's often people finding ways to defeat them, and so this is the thing that started arising in the last couple of years, that they'd find that adding noise, that basically this panda on the right is a panda, this panda on the left is a panda, but the network they trained could not identify this as a panda anymore. It thought it was like some kind of ape, and the noise it added was something about some other animal. So it can have bizarre hangups that you think it's working well in general, but it's actually not generalizing because certain noise can distort it. So ways to combat that are ongoing, people trying to figure out the right way to do it. Yeah, so these ones I don't have. I should get more details on these actually, because I just wrote them down as to-dos. So there's these two problems. And maybe when we talk on Monday, I'll go a bit more on these, and then we'll continue on to convolutional networks in more detail. The idea, there's two other major problems that neural networks have that people try to fix is, oh, I have a better slide here. There we go. Is this exploding, vanishing gradient problem. So the idea is we're doing a lot of multiplications of gradients, which are always going to be some small number, less than 1, and multiplying by a number, and then multiplying by another gradient, and then doing that. And so what if you have a deep network that has like 10 layers deep? Every time you multiply by that gradient going backwards and backwards, you're basically going to get these very small numbers, right? And so as you start doing that, the gradient you're going to get it has this property that sometimes it either like zips down to essentially 0 or infinity, and it kind of just explodes or vanishes, and so it's kind of a real problem that people kind of encounter, especially as the network gets deeper, or the network deals with images and stuff. What was this one trying to show? So different types of networks can be showing no, I don't remember what they're showing now. I have to go look it up. If the gradients are 0 in some places, then you're going to get this erratic output, right? So you don't want to have these kind of we don't non-linearities when we're training, so that it has the ability to make a decision between a threshold of a low kind of probability feature and a high probability one. But if your gradients are coming out to 0, then you can have these periods where it's going to give you very erratic outputs for the values. And so the ways that people have tried to deal with that are by adding more structure in various ways. So I don't know if that makes sense to try to get into that now. Let me see what else I had here. Yeah, because the catastrophic forgetting, that's the last one. Well, we can continue. We'll continue on these ones later. So we'll just give the idea of this, and then people can think about it and read a bit more. And then we'll start here again on Monday and go on to CNN. So this last major problem, which led to quite a bunch of advancements that were very interesting, and it's one of the things I mentioned in the assignment 4, which once you see it, you'll see, is you could try one of these as well as a additional optional thing to try, right? basically, in order to solve some of these different problems, people have come up with lots of different types of neural networks structures. So let's just go to full here. Right now I'm on PowerPoint, so this one. This website had, like, it's a few years ago, but all these different structures. Sorry, I can't see your chat when I do this. So now. Okay, now I can see everything. I think it's a neat way of showing it because there's like so many different types, and they have all these different nodes showing different types of nodes you can have as well. So far, we just talked about simple nodes that basically take all their inputs and all their outputs, and then you train it, right? So this deep feed-forward network, the one here up in the corner, is kind of what they are. Can I zoom? Do you see the zoom? Whoa, okay. I don't know if you really see that. Well, it seems like you do. That's their representation of the simple neural network we have here, where green's just these normal hidden nodes. There's all these other types of nodes that you can do. So basically, there's an infinite universe of ways of creating deep neural networks now. So that's why we're just going to try and introduce ones that seem like critical for all the different areas to search. There's some historical ones that aren't as interesting anymore. So some of the ones that we said to have arrows in different directions are here in this row. Deep belief networks, that's one I was trying to think of yesterday, where the arrows could go backwards. The CNNs that we're talking about, I guess on Monday, are more like this. So they have that node I'm talking about where not all the variables from the previous layer go to the current one because you're trying to use local proximity in the image. So that's these purple convolution nodes. But just about this idea of vanishing gradients, there was a couple ideas of trying to, and of course it's not even listed. It must be. There's many different ways of trying to solve these problems. Even support vector machines, you can essentially re-encode support vector machines with your RBF kernels and represent that as a neural net if you wanted. But the deal with this vanishing gradient problem, there were two major things that came, two kind of parallel solutions that tried to deal with it. Google's solution, and they're trying to solve other problems as well. They're trying to make a network that has more deep layers. One of the problems that happens if you have many deep layers, like 100 deep layers, is the gradients just have this vanishing or exploding problem. So they introduced this inception network, which basically adds more structure. So rather than having a node that just takes all the previous ones, they now have every hidden layer has this different structure, where they take a bunch of the outputs of the previous layer, and then they apply various different sizes of nodes to it. We are talking here about convolutional in general, so that goes around what I'm talking about. You can take that as an idea. We'll talk about convolutions in detail on Monday if you don't know what they are. If you've done a lot of, you've probably seen them a lot in your other like filtering, signal processing things already. They kind of apply that idea. But it relates to that node I was talking about where you have a weight that only uses some of the neighbors as their input, and that's applied as a convolution across all of the nodes. You're learning that filter. So this inception approach basically learns different sizes of those in order to kind of reduce the possibility that you're going to get some kind of zero gradient because you got more variety in that layer. A simpler approach, so kind of was, I think of them as this similar kind of period where they were trying to solve this problem, and it's not tied to convolutions in particular, is this ResNet network. And they basically add more links to previous layers, right? So Here we've got an idea. So if we think of that structure we had before, there's input data coming down from the top in this case. Hidden layer, ReLU, hidden layer, ReLU. You're always only listening to the previous hidden layer, right? So in ResNet, they were kind of saying, well, what if we wanted to have a really deep layer, like 150 layers of this deep network, but the gradients keep vanishing and all that. If we added in gradients from previous layers, basically, further back, and combine them all together, maybe that wouldn't happen, right? So they tried this and showed that you can do it where it gets rid of these vanishing gradient problems, because basically you're not tying each layer isn't just an independent thing that gets multiplied. You tie it into previous layers as well. So they'll add like a link back where like every layer gets the outputs from the layer 3 links before as well. And so even if the gradient here has gone low, you've still got some value from the previous layers, and you build this connection, right? So it feels like they're almost going back in time, but of course there's no time here at all. There's just layers that are basically a bunch of free variables that we're trying to fit, and then the next layer takes those outputs and learns something new. But you can do it where you basically link data from previous layers into your current one. And so you're mixing layers together. You're kind of like merging the signals every few layers, but in this kind of stepped way. And this helps reduce the gradient vanishing problem, I guess, because you're not getting as many zeros. So this example is showing on CNNs as well, but it can be used on any network. Yeah, so that was a couple of those ways of trying to improve the networks. But like I said, so we'll stop there because we got our 10:30, and then on you guys are busy this week finishing assignment 3 and reading on assignment 4 when it comes out. I'm sure you have other things, but start thinking about these. Maybe you do some reading on neural nets or on things like that. And then on Monday, we'll talk about applying them to images and convolutional neural networks, and how some of these more complex structures work.